trend breaks are relatively common, and when you try to forecast after the start of a trend break, it can go very badly wrong if you haven't dealt with it. So the paper suggests an approach to dealing with forecasting after the start of a trend break in the situation that confronted us quite recently for UK annual CPIH inflation, that's Consumer Price Index, including housing. These dotted ones are the Bank of England's forecast starting in February of 2021, shortly after the COVID crisis was dying down thanks to the very rapid production of vaccines. Then that's the next forecast they made. Then in September, and then November. November is getting quite close, but it's only 1 month away from the end of the year. And you could already see that inflation had risen from about 1% to heading upwards to 4.5%. But the initial forecast error is extremely large. But it gets even larger for the first forecast in 2022, which again is in February 2022, which in a sense is bad luck because it's immediately before Russia's invasion of Ukraine, the energy crisis, the food and energy price leaps that happened. And the forecast error is very big, but their other forecast errors are just crazy. They're forecasting 13% with the maximums about 9%. So they're making 4 percentage point forecast errors. The one I'll talk about, which isn't the way we do it, but translated into how the bank thinks about it, is almost exactly correct at the time of just after the forecast, just after the invasion. And then somehow the bank goes from a forecast of 11% inflation to 4% inflation from November through to February. It hasn't got that much evidence that inflation is falling, but it does produce a very accurate forecast. Indeed, it's more accurate than the later ones. And ours is slightly out because we haven't yet picked up this break here. So there are many breaks, and the Bank of England's forecasts are very poor. And on their basis, ours are a lot better, but still not great. But that's not the way we think about forecasting. I think these always forecasting February, then May, and then so on is not the greatest way to proceed for a forecasting agency. So the Bank of England annual inflation forecast was missed badly during the upswing, and they kept missing for a very extended period. That the 3 periods we've looked at, the forecast errors are 2.5 percentage points, 3 percentage points, and 4 percentage points. And this prompted Ben Bernanke's review of how the Bank of England forecast. They were similar to other central banks, but they did continue long after inflation was rising rapidly, and only towards the end, in the middle of 2023, did the bank suddenly push up its forecasts very dramatically. That Bernanke gave 12 recommendations, and these revealed very worrying failings at the bank. And though the bank's response asserts these will be fixed, why did an agency in charge of monetary policy need advice on update and modernize its software and forecasting framework, manage and evaluate its models, incorporate a more realistic representation of the monetary transition mechanism, and include both supply and demand forces? You'd have thought it was blindingly obvious that a central bank should have all of these under control and not need advice to do them. David Aikman and Richard Bardwell's book on the Bernanke report provides very extensive commentary, so I'm not going to discuss them much more, except to say that John Moore and I added to Bernanke's list of problems that the bank needed to address because its forecasting process is subject to breaks, and that's not a theory approach that Bernanke adopted. He did talk to John, but he declined to talk to me. So there's nothing in his report about the pernicious role of equilibrium correction mechanisms in forecasting, not in modeling, but in forecasting, the invalidity of the mathematical basis of dynamic stochastic general equilibrium systems, that it's crucial to test the invariance of policy models before you implement the policy to make sure that the model doesn't change when the policy changes, and therefore the predictions are completely useless. You need to use forecasting devices that are robust after shifts as soon as shifts happen and you detect have happened. And the bank ought to take climate change into account, which wasn't mentioned at all in Bernanke's report, despite the fact that it's becoming a really serious problem for the banking system as well as the central bank. The other thing that was totally missing is forecasting is fundamentally different from modeling, and it need not be based on empirical economic models. And this was not addressed at all in Bernanke's report or in the extensive discussions of the report that Aikman and Bardwell reported. But it will be crucial here and will be strongly highlighted. So the question is, could the Bank of England have avoided misforecasting UK inflation during 2021 to 23? Now, there were a number of unpredictable shocks. The sudden production of vaccines much faster than has ever been possible historically. That's unpredictable. It's a negative shock, of course. Then the supply chain disruption was a very positive shock. The invasion of Russia, by Russia of Ukraine, was a huge shock. And these explain part of their forecast failures, but they reacted very slowly. And actually, as I'll show later, they had bad luck in timing, which also mattered in explaining why bad their forecasts were. So what evidence could they have had? Well, if you get a short sequence, say 1, 2, or 3, large, same sign, one step ahead forecast errors. So you're forecasting 2021-1 to 2021-2, 2021-2 to 2021-3, and so on. As the data appear, you can see that you're making huge forecast errors. So these are occurring as the forecast origin advances, and it signals a sudden shift, because if the model was working before, suddenly it's not working, something must have shifted. If something shifted, you must make corrections to forecasts after they've gone wrong. You can't just say, oh, well, too bad it's gone wrong. Let's just carry on forecasting. It's the same model that isn't working. And that's why we see an important role for univariate models, which use only deterministic variables, no economics at all, just trends and indicators. And we'll show that these can detect breaks in trends very rapidly, and then you can correct the trend shifts from such models. But it's very difficult to do so from large systems when you've only got 1 or 2 observations and you're not sure what's causing the system to go badly wrong. So this is the layout of the paper. Look at trend breaks and relate them to tipping points. Talk about rapid detection and apply it to the UK annual price inflation. Compare that with the Bank of England forecasts. And then I'll explain why it all works. Now, I've worked on intercept corrections in forecasting since 1996. And this paper is based on the fact that an absolutely crucial feature of them was completely missed in all the research that I did or anyone else did in the intervening period. But once you see it, you realize why what we're doing is eminently possible. And then I'll draw some conclusions. The break detection is very widely studied. There's hundreds of tests out there for it in different forms, and they depend on whether it's 1 or more shifts, it's occurred in sample, if so when, close to the beginning, close to the end. But few approaches are applicable at the forecast origin, although Don Andrews tries in his 2003 paper to do so. But then when you actually go on and read what he does, it's actually about 10 or 12 observations in before he's really detecting it. Jürgen has reviewed a range of tests for breaks in trends and compared them to the other ones there. There's a lot of monitoring procedures for structural change, mainly based in Q-sum and Q-sum of squared tests. All these are ones out there, and Bent and co-authors, including Vanessa, consider their application of Q-sum squared tests to models with stochastic and deterministic time trends, as well as nonlinear and non-stationary processes. But for all the sophistication of the analysis, they all take many observations over time to detect that a shift has actually occurred. And the original ones often take 20 or 30 observations before the departure is obvious. Now, once a forecast has gone wrong, that can always be put back on track at the forecast origin by impulse indicators, which act as intercept corrections at the forecast origin, because the impulse indicator will equal the forecast error, and so the intercept correction will equal the forecast error. And Mike Clements and I discussed using intercept corrections and explained why they work in our 1996 paper, but we automatically assumed you'd use step indicators, not impulse indicators. Step indicators differ quite a bit from impulse indicators. But the forecast errors that you're seeing could be due to a very large outlier or a large measurement error. These have all occurred historically. It could be a shift in the mean of the time series process. That's occurred quite a lot historically. Or it could be a break in the previous trend. And intercept corrections can offset all of these forecast errors, but fortunately can be tested against location shifts or broken linear or log linear trends. So the two key questions are, what functional forms could be useful? We'll usually use log t for our applications to log levels in economics, and notice we're actually going to be forecasting log levels, not inflation. We'll derive inflation from the log level forecasts. And how long should you wait until it's possible to estimate? Well, actually 1 to 3 forecast errors is enough to estimate, but you need 2 or 3 to test the functional form is appropriate. Since if you put a log trend into a model when it's one single large outlier, you will, of course, make some very bad forecast errors. So while it's possible to pick it up, you wouldn't want to do it without checking what the functional form was. So we'll use impulse indicators after trend indicator saturation. Now, there are many indicator saturation estimators, impulse indicators, step indicators, trend indicators, and mixtures. There's also cases in which you combine these in supersaturation or ultrasaturation. And the simplest impulse saturation estimator is to saturate a linear model with all the possible impulse indicators, which are all dummies. That gives you more variables and observations, so classical estimation is not feasible, but it's perfectly easy to estimate a model in which you've got as many impulse indicators as observations by simply putting them in blocks. And this corresponds to using a tree search algorithm like Econometrics, and that's been shown to work well. It's flexible, robust, and it can date the significant events. Now, when you've got more variables and observations, you need expanding and contracting block searches that allow all investigators to be all indicators to be investigated for possible significance, but of course you can't do them all. That would take the time to the end of the universe to do it all, given the number of possible combinations. So the details of the research algorithm were in a paper with Jenny, Jürgen, and myself in 2001. Now we're going to be dealing with very high dimensionality. We're going to put 150 data points in the monthly data. Therefore, if we put in all the trend indicators, step indicators, and impulse indicators, that would be about 600 variables with all the variables in the model. So selection must use very tight significance levels to control the probability of retaining irrelevant indicators, particularly if you do them all jointly. Now, the key one we're using are unscaled trends. And Econometrics defines these such that they're zero in the forecast period. So they've no direct impact on forecasts. What they change are the parameter estimates that will go into the forecasting model, but they themselves will be zero. So the first one, tau 2, is -1, 0. At time t, it's minus t plus 1 through to 0. But we don't put in the first two and the last two. So in fact, there are t minus 4 taus going to the search procedure. In this paper, we set alpha at 1 in 10,000 for trend indicator, 5 in 10,000 for cis, and 1 in 100 for impulse indicators. And we select these sequentially using results in a paper that I did with Søren Johansen almost a decade ago. Now, sudden rapid trend changes include tipping points, and it can be hard to discern and difficult to model in their early stages. And tipping points are very well defined these days, where a small change causes a large response, and they've played major roles over Earth's geological past. Lenton et al. Evaluate the tipping elements in the Earth's geological system, and Lenton himself analyzes types of tipping points and their future likelihoods. He defines a tipping point as a critical threshold in the Earth system or related processes which, if passed, can cause sudden, dramatic, or even irreversible changes to Earth systems. This implies that there's not only a shift, but that the previous empirical model has failed because they've changed the way the system works. Hence, it's very important to detect them and then think about how you would update the empirical model. More positively, sensitive intervention points, which are the equivalent on the positive side to tipping points, can help achieve net zero emissions, as Don Farmer and company have shown, and Jenny and I have in a recent paper. Now, since apparent shifts could be due to large measurement errors or outliers, to step shifts in the data mean, or to sudden trend breaks, and since all of these can be corrected by impulse indicators acting as intercept corrections, one has to determine the source. Is it one of these, and which, if so, which one, to usefully forecast? Now, we're going to use impulse indicators to characterize a succession of large, same sign, one step ahead forecast errors. And all three components are important. They've got to be large, they've got to be same sign, and they've got to be one step ahead so they can be exactly matched by an impulse indicator. And this will allow a test of replacing the intercept corrections by a broken log linear trend and test that against step indicators. Once we've gone beyond one such error, we can pretty much rule out just outliers. It'd be very surprising to have several large outliers successively occurring. There are three advantages to our approach. First of all, by putting in intercept corrections, the parameter estimates for the next forecast are exactly the same as the one from the previous forecast, because the model fits precisely at the intercept corrected value. Secondly, as we've mentioned, you can test the adequacy of alternative models of trend or step shift. And thirdly, the approach is model-free. It doesn't depend on the other regressors you've got in the model, because it's just a deterministic trend equation selected by trend indicator saturation to focus on rapid break detection in the log price level. It's complementary to macroeconomic or climate systems using explanatory variables, but these may be hard to update quickly, and it may take you a long time to decide which of them has caused the sudden jump in the forecast errors. Now, we use TIS because that detects earlier broken trends, and therefore major in-sample misspecifications in a trend model can be avoided. And since they terminate before the forecast origin, only the full sample trend remains. See, that's very useful in what follows. The rapid increases in the log price level after 2021 are actually quickly detected, and surprisingly, from two observations, you can provide accurate forecasts up to 17 months into the future. Now, of course, this is not the real future because the forecast is over past data, but it uses none of the future data in the forecast. It's genuine ex ante and could have been done at the time, since the values in the parameters at the time are precisely what we have in the recent estimation of the trend TIS model. Now, it may seem surprising that accurate forecasts can be based on only two post-break observations, but we analyze and simulate that on a separate paper, and the results match the empirical findings of that paper that sudden rapid changes can be quickly detected. Indeed, an example is in our work on forecasting temperature recovery after a large volcanic eruption. And we find it can be forecast with pretty good accuracy for 5 years ahead using just the one observation estimated after the volcano has erupted by a variant of the step indicator saturation approach. So it can be done from one observation, but that's not the kind of case we have here. Volcanoes are relatively similar in their type of behavior. Now, how rapidly could the upswing in UK inflation have been detected? So we're going to look at a forecaster who estimates the model from 2010 month 1 to 2021 month 3. Over this period, there have been lots and lots of breaks, which we'll pick up, but we're not interested in that. We're interested in the bank's misforecasting after 2021-3. So we're going to fit up to 2021-3, then forecast into the future. And we're going to go one step ahead, and then we're going to forecast each month, first of all, 2021-4 from 3, then 5 from 4, then 6 from 5, etc. So we fit the model to this data period. We use trend indicator saturation at 0.30 1 in 10,000. The trends that are reported here are scaled by 100 just for readability. But the fitted value of the log of UK Consumer Price Index, including housing, has an intercept, and then it picks up 10 earlier shifts in 2010, 11, 11.4, 13.4, 14.10, 15.4 and 5, 16.2, 18.12, 19.1 and 19.4. So 19.4 is the most recent one it finds, and it has an overall trend of 0.071, which corresponds to about 0.85% per annum UK inflation. Of course, standard error we'll look at quite a bit. That's 0.2%, because it's a log model. R squared, of course, is ridiculous and doesn't mean anything. There is some residual autocorrelation because we're just fitting trends, deterministic factors. And then the other diagnostics are not significant except for the forecast test from 2021-3 to 2021-4, which hugely rejects. It's an F test of 1,123 of 10.5. In other words, the model breaks down immediately after 2021-3. And this is what it looks like. Remember, since all the indicators are 0 beyond the date at the bottom of the indicator, then the forecast all the time from T to T plus H is just the intercept plus the common trend with the beta 1 hat, which is 0.071. So this is what happens. The last break was in 1991 that we forecast quite reasonably. And then suddenly in 2021-3, forecasting 2021-4, there's a bad miss. The forecast intervals completely miss the outturn. Of course, you don't know this outturn when you forecast. You've been forecasting perfectly well. It's slightly discrepant here, but it was slightly discrepant here and came back. It could have come back down, but it rocketed. So once you see that forecast error, you think, oops, that's pretty bad. But it gets worse. If you go forward yet another month, then the forecast error is very seriously wrong. And if we were to put in our intercept correction, which is the forecast error in 2021-3, which puts the model back on track. So we hit, this is the value here. So the intercept correction takes it up, it's back on track. But the next forecast comes way down and is actually worse than if you hadn't done anything, which is something we can explain shortly. And that will always be the case, or almost always be the case. So now, forecasting with the intercept correction, the forecast interval is way short of where the data have gone, and they've gone shooting up. And this is the supply chain disruption kicking in. But now we've got two intercept correcting values. The one we've already used, and the one we can now use up here. And so we'll have an indicator for 2021-4 and an indicator for 2021-5, and then we can look at them and see what they tell us. And as you can see, what they're going to tell us is it's going up. It's going up very rapidly, and that suggests there's a trend. So if we put in the log of a linear trend, and we always put log, almost always put log trends, because you want a damped trend and the log dampens it, then the next forecast both eliminates the two impulse indicators, are quite insignificant, and is almost spot on that the log trend with a coefficient of 0.0011, hugely significant, takes you straight on. And if we forecast 5 periods ahead, then we get a very accurate series of forecasts. The interval forecasts are somewhat exaggerated because of the recent failures back here. But the multi-step root mean square forecast error for the next 5 observations is 0.15, which, if you remember, the fit was 0.2. So the forecasts are better out of sample after the trend shift than in sample, using the shift trend just from estimated from just 2 observations. And that's the first sign that this general theory is working rather well, and see later exactly why that happens. Now, we can translate these results on the log price level to inflation by subtracting the price level 12 periods earlier. And it looks exactly like you would expect from doing that. This is inflation down at roughly just above 0.5% until the shock. But the forecast is really seriously out for the first period, calculated from the levels forecast, and for the second period, again calculated to 2021-4, predicting 2021-5. If we put in log trend in the levels and calculate what happens to inflation, it's spot on, exactly as it was for the level. And then we can forecast the 5 periods ahead very accurately for inflation, despite the fact that it's gone up, down, and then back up again. But the next observation, this is going to fail. Now, when I show you 5, we actually do 12. But when we get to number 6, we see it's wrong. So we switch the model from being just the previous method of forecasting to allow for another trend shift. And that's what happens here. If we're forecasting 2021-10 from 2021-9, it's again way short of what's happening. Inflation has shot up. And it shot up even more in the next period. If you put in an intercept correction, you just see the same effect back down. But if you approximate those 2 impulses, which are now very big and both shooting up by a linear trend rather than a log linear trend, it's pretty much spot on. And it continues to forecast pretty accurately for the next 5 observations, although the root mean squared error isn't quite as impressive as over the earlier part. It's now 0.4%. It's still very small compared to what you've seen earlier, the Bank of England doing. Now, again, we're only showing 5 because it's already, you can see, starting to go off. And it's going to go off very much more when we try to forecast 2022-4 from 2022-3. And this is, of course, the invasion of Ukraine by Russia. And now the forecast error is astronomical. The Chow test is 63. And it looks pretty silly to say this is your forecast and this is the outturn, but that is what happens. And if we go 1 period further ahead, and I'm not putting in the intermediate ones with the impulse indicators acting as intercept corrections, the next one is also pretty appalling and very, very far short of what happens. So now if we add a log linear trend starting in 2022-3 with the invasion, it eliminates the 2 impulse indicators acting as intercept corrections. It's almost exactly correct for 2022-6. And then, amazingly, as I told you, we just keep forecasting until it fails. For 17 steps ahead from the 2 observations estimating the broken trend, it forecasts without a single serious forecast error until 2023-9, which is 17 steps ahead from the 2 observations estimating the coefficient of the log linear trend. Thus, it's clearly possible to do this sort of thing, and we'll look in a moment at the inflation impact. Remember, all of these trends that we've been estimating are positive. So we've got the first break for the end of COVID, the second for the supply chain disruption, the third for the invasion of Ukraine and the resulting energy crisis and food and energy price explosions. So we've got 3 positive trends. But of course, inflation is going to turn down within those 17 observations. And it might be a surprise, but that isn't a problem for the method. Now, the next significant forecast error would be from 2023-9 to 2023-10. Again, we have another trend break. And this is a trend break on the way down. This time, the log price level, trend has slowed, not going up at quite the same speed. So, can people still see this?
Yes.
Yes. Somehow my I don't know why am I it's not showing any of the people anyway. So if we add a broken log linear trend from 2023-10, again we get very good forecasts, but that's just fitted to one non-zero observation. And guessing that it is another broken log linear trend that's causing this shift. It's not a massive shift, it's only significant at 5%. But nevertheless, we fit a log linear trend to one observation, and its coefficient estimate is minus 0.0104. And if we forecast right through and then re-estimate the model to 2024-3, it's minus 0.0109. So it very much has picked up almost exactly the correct log linear trend. And what all this suggests is a strategy of immediately trying the log linear trend forecast for a logged variable, as well as the intercept corrected one, plus the previous model, forecasting from all three, and temporarily choosing the best as you go ahead. And this is one way that forecasting is quite different from modeling, that you can make all three forecasts in advance and wait to see which of them comes out near the outcome from the same model, but just modeled in three different ways for the broken trend. So how did we do? Well, of course, we missed the first two because we didn't know they were happening, and we had two bad forecasts. Then we got the next 5, and then we missed the next 2. Then we got the next 5, then we missed the next 2. Then we got the next 17, missed the next 2, and then we got the last 5 all the way through. So we've 4 episodes of sudden breaks, but that's actually only one observation, not 2. This looks different when it's flat. And the multi-step ahead forecasts show you could do it extremely accurately. Most of the time, what you can't forecast are the sudden breaks. You didn't know that the upturn after COVID would do this, the supply chain would do that, and the Russian invasion would do this. But you can fix these very quickly. So if we translate that into annual inflation, these are the first 2 very bad forecasts, then we're back in track. And I've put in what happens if you had known at this observation that this was the first estimate of the log linear trend. If you remember, it's not a forecast, but it's a fitted value. Then we get its forecasts. Then we get 2 that are wrong, and then the same thing happens. 2 that are wrong, forecast. And notice we have no problem forecasting the downturn in inflation right to here. Then we miss, and then we get back in track again with that one observation that I've talked about. So the reason it's not a problem to forecast the slowdown in inflation from positive trends in the price level is, of course, they're calculated by subtracting inflation 12 months earlier, sorry, the price level 12 months earlier from the current price level. And that is now higher than the current, than a faster rate than the current one. And so it says inflation is going to be slowing. So our 17 observations come up, go over the top, get the peak, and come right back down again, even though inflation is behaving in a rather different way if you were to think of modeling it by trends in inflation rather than in the price level, which is one reason we include the price level. Now, we need to compare these with the monetary policy report projections that the Bernanke review of the Bank of England was criticising. And the next figure is one you've already seen, but I'm going to go back to look at it again. The monetary policy reports give projections of annual inflation rates over the crisis period. So let's have a look back at this, and then we'll go back a bit. So these are the ones from the monetary policy reports. These are pretty good, and these are fairly similar to ours down to 2024-3, although ours are actually a bit closer. But remember, the first ones, all of them are forecasting the December inflation rate, which I find a very odd way to do forecasting. I mean, why December? What's so important about that? Why not forecast all the inflation rates, which implicitly they do, but they don't need to wait for quarters to do it. They could forecast monthly throughout and be much closer to the way we would do it. And then they might avoid some of these rather crazy forecasts over here, when in fact, inflation's already settled down at about 8 or 9%, rather than 13%, which is one of their forecasts. So our approach was to quickly detect rapid upsurges after large one-step forecast errors to avoid systematic forecast failure. And what the bank has is systematic forecast failure because of its desperate attempts only to forecast December rather than the inflation that's the next quarter or several quarters ahead. The first such shift we found in 2021-4, confirmed it by 2021-5. That enabled a log of the trend from 2021-3 to be estimated and forecast through to 2021-9. Then we detected a second shift at 2021-10. Now, the MPR projection in 2021-2 could not know of either shift. Our first shift was 2021-4. They couldn't have known about that, and they couldn't have known about the 2021-10. So in a sense, it's bad luck. If they'd waited a couple of months to forecast, they could have seen at least the first shift, although you'd only know about the last shift as you got close towards December. But once both shifts are detected, then both of our end-year forecasts were quite accurate. Now, the next shift in 2022-3 was again bad luck for the MPR. It was just after their projection. But detecting it by 2022-5, our approach provided a much more accurate end-year forecast, and in fact through to 2023-9, avoiding these fantastic overshoots. These huge overshoots that the bank has after undershooting, it overshoots. So we can avoid all of those in our approach. Now, Laura Corneo, I've been editing a special issue of the International Journal of Forecasting on the Bernanke report. And one of the papers is by Laura Corneo, and she looks at the bank's root mean square forecast, well, actually mean and standard deviation from which I've calculated root mean squared forecast errors. Now, to get a reasonable approximation to what the bank's doing, I've calculated ours for roughly a 6-month horizon and compared that to the bank's 1 quarter and 2 quarters, or 3 months and 6 months ahead. And our root mean squared forecast errors, which includes all our misforecasting, because we didn't know the breaks were going to happen and nobody could have known they were going to happen until after they had actually happened, we come out at a root mean squared forecast error of 0.7 over the whole sample period from that graph I showed you with all the breaks added in. The bank's 3-month one would be 0.93, but their 6-month one, which is the most comparable, we think, is 1.66. Now, there are slight differences in the forecast periods. We're 2021-4 to 24-3, whereas Laura's are what she calls her second subsample, which is 2019 quarter 1 to 2023 quarter 4. And I've taken her means and standard deviations from her table 1, shown it a shorter and approximately the same average step, but we're even beating the shorter one. Now, our average horizon is based on having 6 forecasts, 5 forecasts, 12 forecasts, 6 and 5, although we could have done 17 here and then 6, and that would have made it a much longer forecast horizon, but I think it's more reasonable to treat it as an annual one compared to the bank. So our average forecasts compared to the bank's 2 quarters ahead forecasts, the bank's 240% larger with 1.66 rather than 0.7. So it really could have done vastly better using a simple trend indicator model than all the complicated paraphernalia it's got for its forecasting procedures. Now, the other thing I can do is compare what's the value added of our detecting these shifts over not detecting. So these are the forecasts you would have made if you carried on with the same model and ignored shifts. And this is for the first one versus ours. This is for the second one versus ours. This is for the third one versus ours, the fourth versus ours, and the final one versus ours. Now, as you can see, there's immense value added. Ours are pretty bad if you go, these are all 12-month forecasts, and indeed, they're pretty bad when you make the 12-month. But of course, before we got there, you would have corrected it and been much more accurate. But for this 12-month period, it's extremely accurate all the way. And for the next 5 months, it misses 2 if you restart rather than take the 13 down and then do 1 more. So there are some advantages to sticking with a model for as long as it would forecast. So there's huge value added in detecting the breaks relative just carrying on modeling them. Now, you wouldn't do that with a trend indicator model, but that does happen with models that are much more complicated and are so difficult to update that they carry on using them. And I think the bank did, which is why it got some appallingly bad forecasts. Now let's analyze what's going on with this break detection. Let the forecast error be the difference between what happened and what you forecast. We assume that there is a log linear trend with coefficient psi, which starts at any observation beyond sample size t, which in our case is, if you remember, 2021-3. And this is a linear trend equal to t minus capital T plus 1 when t is greater than t, and the error is going to assume independent normal, not sigma squared. Now, the break's not known at t, so your unadjusted forecast would simply be the in-sample estimate of the linear trend, and the forecast error would be the difference from the true coefficient of trend, the error from the log linear shift, and the random error at the end. Now, I'm going to assume that our estimate of the trend for the whole sample is unbiased because we've dealt with all the trend breaks, and it is a negligible variance because it's a trend. And so we can say that the expected value of our forecast error is psi log 2, and the variance is sigma squared plus psi log 2 squared as the mean square forecast error. Now, the next forecast is after adding the impulse indicator equal to the error you've just made. And so the fitted value at t plus 1 is your forecast that the fitted value now, plus your intercept correction. Now, the intercept correction is equal to this key equation, which until a previous paper last year, I had not noticed that what the intercept correction is doing is, let's assume this is essentially 0 and the error is just a random thing. It's actually picking up the log trend. It's a one-off single observation, but it's got psi log 2 if there is a trend break. Now, Mike and I didn't notice that. We are focusing much more on the fact that intercept corrections difference the data and give you much better forecasts. But we didn't pick up that it's collected the estimate of the new trend. So when you put in that into the model and you add the log trend, it removes the intercept correction because it's only deviating randomly. Since log 2 is 0.69, then the intercept correction divided by log 2 is an estimate of the trend coefficient. And now your intercept correction moved forward with a log trend is the correct estimate of the trend plus the shift. And consequently, I'm not going to go through the algebra because I see I'm running out of time. That's an unbiased estimate. And so the mean square forecast error becomes sigma squared from one observation that this impulse indicator picks up because it picks up the log linear trend. And that suddenly explains why all of this works. Impulse indicators, actives, intercept corrections are always picking up the log trend times coefficient. So if you put in the log trend, lo and behold, you get the coefficient, and now you can forecast almost unbiasedly until the next shift, which of course keeps happening. And the final break in our sample, psi bar was minus 0.007, and the trend coefficient is this, which is exactly that number divided by log 2. And the resulting mean square forecast error stays approximately at sigma hat squared at that level for the remainder of the forecast horizon. Now, of course, you need that there really is a new log linear trend. That's why you need several observations to check that that's what it is, even though you can estimate it from one. You need several to test that it is that, and no further breaks occur. Otherwise, for an outlier measurement error step shift, the forecast could be much worse, and that's why we tend to use 2. So the Bank of England only started raising interest rates from 0.1% in February 22, continuing in small steps till 5.25% in August 2023. Our accurate 17-month ahead forecasts, albeit ex post, but they're ex ante relative to information, to 2023-9 were made from 2022-4, and that's before any of the bank's interest rate forecasts. We wonder, had we done this, had we known that we could do this before 2022-4, which was perfectly possible, we just didn't happen to know that this could be done, the same forecasts would have been made. And I do wonder what the MPC would have made of them. They're raising interest rates from nothing to 5.25%, killing mortgage holders with high interest rates and putting up the cost of the national debt, etc., and having no impact on a forecast of inflation 17 months ahead before they start all of this. Now, John and I estimate the impacts on UK inflation in 2022 of import price inflation, energy shortages, and fuel price rises of 140% to be about 3/4 of the peak 9% rise. So all of those external influences dropped considerably in 2023, and that's why UK inflation rose more slowly, not what the bank is doing. The other set of conclusions is time series data are highly non-stationary. From stochastic trends and locational trend shifts, forecasts are uncertain and prone to failure because of unanticipated shifts, but these cannot be avoided. And so it's more important, actually, to have a method of taking account of them and get forecasts that will rapidly detect the break and reduce the large forecast errors by booking linear or log linear trends. Thank you. Hi, Christian.
Hi, thank you for the great talk. I would have first a clarification question that I really understand correctly. So you're running at each time step, you run the 3 models, and then you look at the point ahead, which has the lowest forecasting error, and then you take for the next period the one which had the lowest?
No, we don't, but you could.
Oh, okay.
Right. What we do is we take the model and we make the 1 step ahead forecast. And when it's significantly bad, we put in the intercept correction to correct that and make the next 1 step. And if that's also even worse, we now know it's a trend. So we then put in the log linear trend.
Okay, and then you use the log linear trend as long as this happens again.
Yeah, so long as it works. And then you come to a point where the next 1 step ahead, you may have forecast a year ahead, of course, but you don't know that until you get there. But after 6 months, you discover it's gone wrong. And so you now need to put in another set of procedures like that.
And then my actual question would be now, following up on that, you say you could forecast 1 year ahead, and probably if a central bank would use that model, they would do so a year ahead or even longer, right? Because they have a long-term interest in the policy. How would you, or I mean, ex ante, you don't know how long the trend will last, right? On which you're riding.
Not a clue. You've never got an idea of how long any of these models will last, whatever kind it is.
But how you would interpret it is, okay, as long as there is not another structural break happening through like the war or the supply chain problems or so, that's likely what will happen. And if you have a structural break, then anyway, you need to think from anew.
Yes, So in fact, one of the features of the big models is they all work when you don't need them. Namely, nothing happens, in which case they work. But as soon as something big happens, they don't work and they need corrected. Now, some models go very badly wrong when there are step shifts, like DSGEs, whereas others, like a trend model, you can fix in 2 observations. But fixing a big model in 2 observations is not going to be possible. It would have to be ad hoc.
Okay, very great presentation. Thank you so much.
Okay, thanks.